Okay, so this week we're going to start looking at linear programming. So, sounds super fancy. It's actually very similar to what we've been doing with graphing systems of equations or inequalities. So, linear programming, if this will go, linear programming is a way of solving problems involving two variables with certain constraints. So, these types of problems ask for a minimum or a maximum value of a certain output. Depending on the two variables. I need to fix that typo there. So the most common example of linear programming is related to a company that must allocate its time to creating two different products. The products require different amounts, another typo, of time and money, which are restricted resources, right? That makes sense. Hopefully time and money usually are very restricted. Time, definitely. We only have a certain amount of time. And money, usually there's only a certain amount of money that companies want to put toward a product. And with time can't be negative, right? So, and cost is also probably not going to be negative when we're thinking of that. That's going to grow with the project there. And they can sell the items for different prices depending on, what time and money is put into them, maybe different qualities of the item. So in these problems, linear programming can answer the questions, how can this company maximize its profits, or how many hours per week to work on these items to minimize the cost. So we can answer these questions very quickly with linear programming. So what does it look like? So first, here are the steps. So the first step is to identify the variables and the constraints. And this is in a word problem. If you're given a problem, which is the first couple we're going to practice here, we're going to be given the constraints like this. So in a word problem, we have to identify these. And then the next thing is to find the objective function. So that's the actual equation that they give you. And in a word problem, you may have to write this equation. But for the first one or two, I believe they're going to give us the equation. So this is the objective function. So once we graph the constraints and identify the vertices of our polygon, it's either going to be a triangle or a quadrilateral. It just depends on how many constraints we have and how they cross each other. The actual polygon that's created, how many vertices we have. So in this one, I can see there's 4 corners here that these lines, these inequalities would cross. So if we think about these really quick before we move on to that fourth piece, because that's how we find, the minimum or the maximum, depending on what they're asking us in the problem. Let's look at these constraints. So with this one, y is greater than or equal to 0. X is greater than or equal to 0. So these are very basic constraints on these types of problems, and we can kind of go back and think about time and money. So if we had time along the x-axis and money along the y-axis, so time and cost, it makes a lot of sense that time is going to be positive. It has to be greater than or equal to 0. I can't have negative time. And then y, if that's my cost, well, it's not going to be in the negative. Cost is going to be positive. It's definitely going to cost me something to make these items. So those are very basic constraints that probably have to do with something along the lines of time and money. Not a promise, but generally that's kind of where they land. And then with these are going to be the actual inequalities for the items. So if I have 2 items and say I want their, let's see, I'll say, I don't want to say iPhone because it's small. Let's see. We'll say nice pens and for like teacher pens. I'm sure you guys have seen us using those like nice felt pens or, the really nice ones. Pens can actually get really expensive. So I have pen X and pen Y, and together they cost me $6 to make. Or I have pen X and pen Y, and the difference of the two is going to be $4, or it has to be greater than or equal to $4 for the difference. So I have a kind of a nice pen, and I have a lower quality pen. So we have these 2 constraints, and then I go through and I graph them just like I would any other inequality. So for x is greater than 0, I just find x. So x greater than 0, that's, remember, right and left. So that's that orange line. So I would put an orange line straight up and down, and it's going to be a solid because it's equal to. And I would shade everything to the right. Now, they're not showing me all the shading. They're only showing me the spot where all the graphs cross. but it would be the entire right side would be orange here. And then for y is greater than 0, so I go back to this 0, 0 point. Well, remember y is up and down, so greater than 0 means up. So I put this purple line. It's kind of hard to see on top of the black axis line, but there's a little bit of a purple line there. And then I would shade everything above this line. So right now, this quadrant would be completely shaded. The other areas might be shaded. So there would be shading over here, down here, that would be orange, and there would be shading over here that would be purple, but we wouldn't actually use those two areas because they don't cross. Now I have to go through and I have to graph these ones. So the easiest way to graph those would probably be to turn them into slope-intercept form. So, you'd subtract x from both sides and then make sure you deal with this negative as well. And then you can graph those two lines. So we can see here's the blue line, here's the green line that they graphed for us. And we're going to practice this in just a moment, not just talking through it. So now I've graphed my 4 constraints. And I know this blue area is where all of those graphs come together. And I have to find a solution within that graphed area, within that kind of shared or common solution area. So the way to find minimums and maximums is to actually look at the vertices. This is how we're going to find minimums and maximums. So any point within the shaded area is going to be a solution, but specifically to find a minimum and maximum, it's going to be one of those vertices. So I'm going to look at all 4 vertices here. So I have 0, 0, that's the first one. And then I have 0, 6, I have 1, 5, and 4, 0. So you can see here are the 4 coordinates. And what they're going to do with this objective function is literally plug in the coordinates. So instead of x and y, I have 0 and 0. So 2 times 0 is 0, plus 0 is 0. And then the next one, I have 0 and 6. So I have 2 times 0 plus 6. 2 times 0 is 0, plus 6 is 6. So I'm just plugging in the vertices to that objective function 4 times. And that's my 4th task. That's how I'm going to find the answer to the question they're asking me. And I go through, depending on whether they're asking me for minimum or maximum, that's what I need to focus on. So we do have to pay attention. What are they asking me for, minimum or maximum? All right, so let's go ahead and actually try a problem here. There we go. I don't know what it was doing there. All right, so before we jump straight into the problem, I want to put out there graphing calculators can be very useful for these types of questions because it's essential that the inequalities are graphed correctly to identify those vertices. I like Desmos.com. It's one of my favorite graphing calculators online. By no means the only one. Alex will also provide graphing calculators for all of these, so you can use Alex right there on the program. Some of the problems will give you a graph where you can graph it as part of the answer, and some won't. So it kind of just depends on which one you're working on there. But you can always use Desmos.com, and in fact, like during state testing, Desmos is used quite a bit. So getting used to that program would be a very good idea. So the very first thing to do, because the constraints are already identified, that was actually step number 1 on the notes page there, but they're already identified for us. So we're going to find the maximum value of the function z equals 6x plus 2y subject to the following constraints. So here we go. We have the following constraints, and it even says, note the Alex graphing calculator can be used to make these computations easier. Definitely use a graphing calculator. You can also use graph paper if you want. Just be very careful, very accurate when you're using graph paper, because if you do the line even a little bit kind of off, then you're not going to find those coordinates the way you need to. So just be careful, or be specific, I guess is a good way to say that. All right, so the first thing we're going to do, since the constraints are already labeled or already identified for us, is what is our objective function? So we're just going to identify that equation they just gave us, z equals 6x plus 2y. So this is what we're going to use down here in the table once we know what our vertices are to find our maximum value, because that's what we're aiming for there. All right, so now we're going to graph the 3 inequalities. I like to use different colors because as you use different colors, especially if you're doing this on paper with like highlighters, you'll be able to see the different areas very easily, especially if you're using colors that kind of work nicely with each other. Like blue and red are going to mix to make purple, or orange and red, or not really red with a highlighter, more like pink, but orange and pink, yellow and pink are going to mix to make orange, things like that. So you can definitely look at those ones, or yellow and blue will make green. So that's kind of basic art stuff there, if you've never seen the mixture of colors. So that's always kind of fun when you mix colors. But it just makes it very easy. You do not have to use highlighters. You can use a pencil, just kind of shade in different directions so that you kind of have this cross-hatching thing happening, and you can kind of see very easily where the sections are mixing. So to graph this one, I'm going to go to X for 3, because it needs to be greater than 3. So I'm going to go 1, 2, 3. So this is where I'm going to put my line. So this is the point where it can't go back. It has to be greater than this point. So my shading is going to be that whole side of the screen there. And I'm going to clean this up in a moment so that you can actually see the constraint area a little bit better. But for right now, this is the whole red area. So anything in this section would satisfy this one equation. So now if we look at y is greater than 2, I'm going to do this in blue, and I'm going to go 1, 2, and there's greater than 2. So it's going to have to be above this line. So it's greater than. So with these ones, it's not greater than 0, which was the example one we looked at. But maybe in this case, if it's time and money, maybe to set up the situation, you have to put in at least maybe 2 hours or 3 hours for X if we're looking at this as the time. So maybe there's a minimum of 3 hours. No matter what, I have to get to this point because maybe there's some kind of setup to make this item. And then same thing for the 2, the cost, maybe the setup, no matter, since I have to set up, it costs this certain amount of money or something along those lines. So there could be a reason why it's lifted up off the 0, 0. All right, so now we're going to look at the third equation there. And I'm going to do these type of things. Instead of looking in at y equals mx plus b, I'm going to solve for 2 and 3 because I want to know when it crosses the red and the blue line here. So with this one, the reason I'm not doing y equals mx plus b is because I would end up with decimals. Now, if you're using the graphing calculator, it's not really a big deal because it's going to graph it very nicely for you. So it'll definitely show you where those points are pretty quickly. But if you're trying to do this on paper and you're using decimals, that's when it gets a little bit iffy. That's where we can't be very specific. So that's why I'm trying to do it a little differently so that we can kind of see when y equals 2, what does x have to be greater than or less than in this case, since it's a less than sign. So I say y is equal to 2, so I plugged in 2 here for y into this inequality. So 6x plus 2 times 7 is less than or equal to 74. Multiply the 2 and the 7, and I get 14. I'm going to subtract the 14 from both sides so that 6x is by itself, and that's going to be less than or equal to 6. Oop, and that popped up a little quick. I clicked the button, that's why. And then we're going to divide by 6 on both sides to get x by itself, because anything divided by itself is 1, right? It cancels out. That's the whole goal of this whole idea, is that we're canceling things out. So 60 divided by 6 is 10. So x has to be less than or equal to 10. So I know that the point is going to be right here. It's going to start right here, and it's going to be less than that point. So it's going to have to come this direction. So now if I do the same thing with x, so when x is 3, so now I'm looking at when it's on this red line, where does that the third constraint have to land? So now I'm doing 6 times 3 plus 7y is less than or equal to 74. Again, just using the same equation. I just plugged in 3 for x so that I can see what does y have to be less than or equal to. So we get 18 is plus 7y is less than or equal to 74. I'm going to add 18 to both sides. So the 18's cancel. 7y is less than or equal to 56. And then we get 8 when we divide the 7 away here, right? Because 7 divided by 7, that leaves us with our y. 56 divided by 7, that's 8. Okay, so now we're going to go ahead and graph the line. So I'm going to put the line from 10 for x to 8 for y. So it's just a way of putting these on here. Oh, I need to change that word. I changed the color and I forgot to change the word. So it's not pink. It is green. The line is still kind of pink though. So I'll change that up just so that it's the correct word. But this shows me that I know it's this section because it's less than 10, it's less than 8. So I know I'm going to be shading on this side of that pink line that I'm going to change to green. I changed it to green to make it a little bit more identifiable, because when it was pink, it kind of sort of was identifiable, but it just kind of was a darker pink. This one, you can kind of see, here's green, here's kind of a blue-green. This is kind of a weird reddish, greenish. I'm not really even sure what color that is. Kind of a little bit more brown. And then this one is getting a lot darker. This one looks like a tan color because they're all starting to mix together. So this is actually the section that we want. This is our constraint area. So when we look at this, here is our constraint area, and I will clean up these colors so they're all consistent once we actually get over there. So this is the area that we actually kind of want to pay attention to. The rest of those areas that were shaded all around that don't work. They only work for one or maybe two of the constraints, but not all three. So this is the only area that works for all three constraints. Okay. So now we're going to identify the three vertices and use them to find the point that will result in the maximum value, because that is what the original question asked us to do. If you've noticed, I had a little mistake to fix there. So I changed this to green instead of pink, and the line is now green, and the little section area is that kind of weird brown color that it ended up turning into in the last slide there. So I was trying to match that as best I could. All right, so the three vertices that we have, I can see I have a corner, a corner, and a corner. That's what a vertex is. So this first one, and I'm just listing them all at the same time, but it's 3 and then 2. That's my first one. And then it would be 3 and 8. And the last one is going to be 10 all the way to the side here, and then 2. So that's where I got those three vertex or vertices, just showing that those are the points that we're going to test. And this is the objective function that we're going to plug these points into. So I have z equals 6x plus 2y, so instead of x, I'm going to put 3, instead of y, I'm going to put 2. So we can see that happening right here, and I'm going to multiply. So 6 times 3 is 18, 2 times 2 is 4, and I'm going to add 18 plus 4 is 22. So I can't answer the question yet because I have to do all three of these. If there's 4, I have to do 4. I have to do all of the vertices before I can answer the question, what is the minimum and the maximum? So now I can go 3 and 8. So I'm plugging in 3 and 8 instead of 3 and 2. So 3 times 6 is 18, 2 times 8 is 16, and then I'm going to add, and I get 34. So this is definitely a larger number than 22. So if I'm looking for a maximum, I already know it's not going to be the first one, maybe the second one. Let's test the last one here. So I'm going to plug in 10 and 2. So 6 times 10 is 60, 2 times 2 is 4, and then 60 plus 4 is 64. So definitely this one is going to be my maximum. 64 is the largest result that I ended up with. So my maximum is going to be 10, 2. So z equals 64 is the maximum. This is what they're looking for when they ask you what the answer is, just z equals 64. They're not actually asking you to identify the coordinate, but you need the coordinate to answer this question. So it's definitely very important to understand what you're being asked, identify your pieces, and make sure you're paying attention. Am I looking for minimum? Am I looking for maximum? This one doesn't have any context to it. We will work on word problems on the next video so that you actually have some context on how to build an equation like this and what it might mean. So I hope that helped with linear programming, kind of an introduction to it, and I will see you in the next video.